I decided to sort of put together what I thought was interesting for the mathematicians, and so sort of a grab bag of topics. Just leave it at that. So let me start off by saying I'm a metallurgist by training who got into this field of electron microscopy, and in metallurgy, electron microscopy is key because it's how we describe the structure. And oftentimes it's very difficult to describe what the structure is. We call it microstructure, material science. And you can see here the microstructure exists at many different levels, and it's incredibly important for relating the properties of a material. This is rhenium, maybe a metal you haven't heard of. It's an amazing metal. It's the second highest melting temperature of any element, and this metal basically doesn't care what temperature it is, deforms the same way at every temperature, and it's an incredibly important metal for aerospace. This is what it looks like at the atomic scale. You got these really fine twins. A little bit larger, you can see the twin networks, and then even larger, you can see the twins inside, grains. And so every different length scale, how do you describe this quantitatively? At this length scale, there's a technique called EBSD, which is what this color picture is, electron backscatter diffraction. That's probably the most quantitative technique exists in material science for describing microstructure. It's incredibly good for quantifying microstructure. But it gets harder and harder to really do that in a way that's useful as you go farther down. And what I'm going to talk about today is really 40 STEM, a technique that we've been working on at Berkeley for a while, and how 40 STEM really helps you quantify across this whole length scale bridge here. In terms of why it's important, in material science, we have what's called the material science tetrahedron, which relates performance and properties to the structure and the processing of a material. And you can see here, this is I've been working in the field of titanium metallurgy for a long time, and these are essentially nominally almost pretty pure element titanium alloys. And you can see the structure varies a lot, and how the structure changes the properties is also very dramatic. So you can see here, these are what's called stress strain curves. So how much stress do you need to pull at a certain amount? And you see there's a huge discrepancy here across these systems, whether it's temperature, whether it's teeny bits of differences in composition, and a lot of that's related to the structure. So how this structure evolves determines how far you can pull this material. And so again, trying to quantify this structure, how do you quantify that to relate it to the properties? And maybe one of the best examples of this is a work we did a few years ago, or 2 years ago, on cryoforging of titanium. It made the cover of Science here, as you see. This was actually a very good example of just pure microstructure and how microstructure changes the properties. Because this was all done on absolutely pure titanium. No additives at all. It's a pure titanium. We got it from Tymet, titanium manufacturer. It's the most pure titanium you could do. And what we did is we put a special microstructure into this material. We started with a relatively large grain structure, and we compressed it at liquid nitrogen temperature in 3 different directions, putting in this really dense twin network that you saw, these little lines. And then we annealed it to get rid of dislocations, but just leave behind the twin structure. And what that did is it gives you this microstructure that has these twins in it, as you see right here, with no defects inside. And what that means is this perfect skeleton for what's called work hardening. Because if you have lots of defects inside, that leads to a lot of stress concentrations. Twins have relatively low stress concentrations, but they're really good barriers to deformation. And so what it does is it takes your stress strain curve, as shown here, room temperature, the red curve, turns it into the orange curve. But even more impressive, the green curve is what it would look like without the cryoforging at cryogenic temperatures, and the blue curve is what happens at liquid nitrogen temperatures with this microstructure. So this is purely a microstructural effect, and you can pull this bar of titanium 100%, which is a huge number for a metal. So you can basically strain it the exact same length that it started at. And that's only through microstructure. And again, how do you quantify this microstructure? There's all different length scales, and we sort of did the best we could here. So you can see that this is across 5 different length scales here, and we did some statistics, and we said, okay, this is the sort of grain size you get from the EBSD. The micro twins you can also get from EBSD, but the nano twins that are, almost atomic, just a few atomic rows small, you really can't get from EBSD. You can only get that from a high resolution electron microscopy. So again, the quantification is incredibly important. And 4D STEM is one way to do that. And so 4D STEM, Colin talked about it yesterday, other people have talked about it a lot, so I'm not going to go into too much detail, but what you're doing is you're just trying to capture all the scattered electrons you can. Instead of a conventional bright field or dark field where you use an aperture and you block a lot of electrons, you actually collect everything and you can analyze it afterwards. You can make virtual diffractions, virtual dark fields, you can analyze in all different kinds of ways. I'll show you a couple examples of how we've done that over the years. So Colin talked about this yesterday too. Strain is a relatively easy thing to do with 4D STEM. If you can find the centroids of the diffraction disks, you can relate the dimension, the diffraction vector to a lattice vector, and then have it relative to something, and that gives you strain. And so this is, for instance, one of the first strain maps we made of a multilayer. In every pixel here, we have a diffraction pattern, and we can colorize that pixel based on the dimension of those lattice parameters. That's really a sort of a simple approach, but also very powerful, something that's very difficult to do over that length scale in any other way. So you can also do this in situ. We've done this while deforming the a sample inside the microscope, and so you can get a stress strain curve and also relate the variation in strains and stresses across a gauge section of the sample with 4D STEM. You can use it for statistics. So this was a paper we did where we just looked at orientation analysis of catalytic nanoparticles. So you get these catalytic nanoparticles all over the place, and you just take huge amounts of data and try to quantify the orientation of different grains inside these catalyst nanoparticles. And lastly, here was an example we published last year, or I guess this year, with a group from Stanford, from Will Chu's group. Colin Nofus and I worked with Will, and we looked at the correlation of lattice parameter, which is measured with 4D STEM, and lithiation, which was measured with X-rays at the synchrotron, and the same exact particle. So we took the same particles from the synchrotron of the ALS over to NSEM and calibrated essentially Vegard's law, how the last parameter changed with composition as this battery nanoparticle was being cycled, lithium's going in and out. And so this is, again, a length scale where there's something going on, and it's really hard to quantify it without something like 4D STEM. So I also want to talk about soft materials. This is an area I think is really interesting, especially for maybe mathematicians that could make an impact in how we quantify them. This is a block copolymer, and of course you see the main problem with soft materials in a TM is, as you see from this movie, they start to fall apart, and there's of course beam damage, all different types of beam damage. And so you're fighting beam damage while you're also trying to quantify something like this, and you don't have a lot to work with oftentimes because these materials are oftentimes similar compositions, carbons and oxygens, and it's not, it's oftentimes only partially crystalline or not crystalline at all. And so you don't have the types of scattering that are easy to quantify like I showed you with the metals. So in soft materials, you have to do things like, of course, do experiments at cryogenic temperatures to try to minimize the effect of the beam damage. You can't really turn beam damage off. You can just minimize the effect by cooling down your sample. There's other things you can do to really increase your resolution with soft materials. One thing that we've done at NSEM is use these small apertures. Colin talked about yesterday the patterned apertures, but you can use small apertures too to help you get much crisper information for these types of techniques. And then of course you have all these scan parameters in STEM that are at your disposal. And this to me is one of the reasons why 4D STEM is actually so useful for soft materials. And the reason is because you can't actually very easily predict what the beam tolerance is of a soft material, a polymer, or organic material before. Biologists like to say, okay, proteins, you need less than 5 electrons per square angstrom. that's a rule of thumb. I mean, some things last a little bit longer, some things don't last as long, and it's really difficult to predict. So what 4D-STEM gives you is this great parameter space where you can just take lots of data with different parameters and take the best data set that you can at the very end without a priori knowing what the beam tolerance is. So for instance, you can undersample or you can oversample. You can change the spacing of the step size. You can change the probe dimension. All these things give you differences in how the sample is dosed and how the damage accumulates as you're rastering across your sample. And so I think this is one of the reasons why 4D-STEM is so useful, because you get lots of different attempts at changing that parameter space, and then in the end you can just take the best data set you can. So that's our approach with soft materials, and that's what we've done. We usually take lots of different data sets, different step sizes, et cetera, and then take the best one. Colin talked about this example yesterday where we had a partially crystalline, semi-crystalline organic thin film used for organic electronics. You can see the scattering is very weak, but it's still good enough where you could pick up the spots. And by doing so, and Colin showed this yesterday too, you can have data at each point that you can quantify. And the first type of visualization that we did with this is something that Colin came up with, which is this flow line analysis, where it takes this grain structure here, but it also takes the idea that we know these are molecules that are tied together. So it's not just the orientation of the grain, it's the fact that these are backbones of molecules that are tied together. And that allows us to essentially draw these lines that map the molecular arrangement of these small crystals. So this is something we did a few years ago to visualize with 4D-STEM soft matter. Since then, we've started to work, taking this a little bit further. This is a paper that we just published in the spring, where we took this a little further and we wanted to look at a composite material that is both crystalline and amorphous. So the film I showed you before also has amorphous regions, which we just ignored and we didn't do any analysis about, only looked at the crystalline part. But in this case, we have two very beam sensitive organic thin films that are sort of partially crystalline. There's little crystallites inside, and there's also amorphous networks. And we wanted to look at, in this case, we were working with Dow, and we wanted to look at the interface. And if the interface, if there was bridging across the interface of these two polymers, or if there was a difference in the crystals on each side of the polymers, for example. So I'll show you our analysis here. So this composite was called, it's polypropylene, and a material called Engage that Dow has, a proprietary material. But they're basically both polymers. They're supposed to be sort of incompatible, that's what's sort of interesting about them, but they actually do a very good job of sticking together. And so we wanted to look across this interface at the structure. Again, really weakly scattering. You have to do the experiments at cryogenic temperatures or else you get nothing. You have to have a very low dose. And again, what that dose is depends on a lot of parameters. And we just vary the parameters until we get the information that is still there. This is what the scattering looks like at each point, really weak. And this is, for instance, what a bright field 4D-STEM looks like. Nothing. You don't see anything. This is what dark field looks like. Again, nothing. You don't see anything. You've got to do something else just to help you understand and quantify this microstructure. So one thing you can do is you can take a radial profile of the amorphous scattering. So there's an interface in here. You don't see it, but if you just did a radial profile at an average at each point, you would see that on one side, this red side here, the polypropylene, you get this radial profile like this, and on the blue side, the Engage, you get the radial profile like this. So you basically take a virtual detector to accentuate these two, and you basically can now visualize what was before. You couldn't see which side was which of this interface, and now you can actually see which side's the polypropylene, which side's the other part. But there's a lot more to it, because all this is a radial profile. But there's little crystallites in here too. And so that's the other thing that we wanted to pull out. Okay, it's just the same thing. So the crystallites, you can see, not just from the radial profile, but see from actual scattering diffraction vectors. And again, we sort of took this idea that, okay, let's not just map the direction of the scattering vector, which is mapped in color, shown here, but let's also take into account the fact that we know that these crystals are bigger than 1 pixel in this case, and that if we happen to have ones that are next to each other in the same orientation, that must be the same, single grain. So we developed this seeding algorithm that would, say if a pixel next to me had a similar scattering vector and within a given tolerance, I'm going to color it the same thing, and then you can seed each pixel, like you can seed the different crystals. And so now you can start to visualize the crystals. The interface is right there, and you can sort of say, well, is there some difference in the crystallinity near that interface? In this case, there really wasn't. You can overlay it here on a grayscale of the different structures. You can get a lot of information here. A lot of this is basically showing us there isn't much difference between anything at the interface and anything far away. You can measure the interface width, for instance. You can see the local amorphous scattering. You get the interface width, diffraction information, the statistical in-plane information. And so in the end, you can put it together, and this is our sort of best version of this. This was a lower mag, so it's a little bit less beam dose. It's a very small beam dose, so that you actually can get the crystals inside the polypropylene side. And so what we've done here is visualize with 4D STEM. You can see the two phases, the two phases here. You can also see the crystals. And we've colorized them differently, whether they're in polypropylene or whether they're in the gauge side. And so you can really get an idea, is there any difference in the crystallinity near the interface or not? We don't think there is. Is there bridging? We don't think there is. And so in the end, we aren't really able to see much difference near the interface, but at least we can now quantify this microstructure in a way that you really couldn't before. And I don't know any other electron microscopy technique that could show you this type of information from this really beam sensitive material. Here's another recent example from some work on a polymer. This is a conductive polymer in lithium ion batteries. This is work that actually just got accepted in Nature Energy in collaboration with Gao Lu. And Colin and I worked with our postdocs on this analysis. What they had is this conductive polymer that they annealed, essentially. And they annealed it, and around 500 degrees, you see this big transition. And they had hypothesized that what was happening was they start with a structure that looks like this cartoon in the middle, shown here, where they have a conductive polymer and it's got all these side groups, what they call higher order structures. These things are used for like adhesion and processing, help with the processing and stuff like that, but aren't really useful for the conductivity part. And so what they essentially were doing is cooking these things off about 500 degrees. And so you get left behind just the conductive polymer, and a lot of these side groups, which are useful for the processing but not for the properties of the battery, are sort of cooked off. And so they wanted to visualize what was happening. 4D STEM, of course, was what we used. And you can see right here, basically what's happening. At room temperature, you have amorphous, purely amorphous. You don't really see any crystallinity here. As you start to anneal it at 500 up to 650, you see this crystalline blob type region start to appear. And here we're mapping the flow line basically just on the direction of these blobs, as shown here in this analysis. Interestingly, here's the data just shown on a simple plot. This is the Q, the scattering vector here, over the temperature range of these samples, how they're annealed. You see in the beginning that there's a really wide spread in Q value. That's right over here, really wide spread. And as you start to anneal it, the spread tightens up, and you get just these, really a blob that is well characterized by a certain Q value. And what's actually interesting is as Hadass very recently did this in situ too. So this was before, these were different samples, all annealed ex situ and taken into the microscope and done with 40 stem. But actually we're able to show the same data and the same trend by actually taking a film in situ in the TEM, heating it up in situ, and you actually get the same exact, essentially representative data, which I thought was interesting. These are different, so it is still beam sensitive. So these are the same film, just 40 stem examples taken from different areas of the film at different temperatures. Okay, so this is a way of, I think quantifying microstructure in a polymer that's really useful. I mean, what's interesting is our collaborators came to us and they had something like this and they had the properties of the polymer, but they didn't know what was going on. And X-ray scattering really didn't show it. Because X-ray scattering, imagine you take these blobs and you average all the different orientations. It looks a lot just like that amorphous scattering, right? So it's really the spatial resolution of 40 stem being able to take individual crystals that actually shows you the microstructure. So the X-rays don't show, I should have shown that plot here. The X-rays really don't show anything like this. And so it's really, that's the power of this 40 stem technique. So, okay, so I want to now turn to one last topic, which is short range order in metals, and talk about how 40 stem is useful in looking at microstructure there. So short range order is a term that has to do with local ordering on a crystalline lattice. So for instance, a typical example is in titanium alloys. It's you oftentimes have additives like aluminum or oxygen or nitrogen, and the base lattice of titanium, alpha titanium, is HCP, crystal structure shown here. And the question is, these aluminum atoms, you put a little bit of aluminum in, let's say 6%, do these aluminum atoms go anywhere, or do they actually order? Do they form order structures? Do they prefer not to be next to another aluminum, for instance? And whether they order or not has a big effect on properties. One of the biggest effect on properties, and this is sort of ubiquitous across a lot of alloys, is this idea that we have ordered structures, you end up with this feature called planar slip. So here's an old picture from stainless steel. Here's a picture from titanium, and you see the same idea. These lines are dislocations, right? Missing rows of atoms. And what you see here in this feature of these alloys that show ordering is this planar slip, meaning the dislocations like to follow one another along a single slip plane, a softened slip plane. And in alloy design, that's not very good. And the reason is because when you want a material to deform, you want defects to go all different directions, get tangled up. That's called work hardening. So you want them to go in three dimensions. You want them all to go different directions. This is bad. This is all following one another. That means they follow one another and they hit something and they create a stress concentration that leads to a crack. And so this is usually thought of as bad for properties. And it comes about because if you have an ordered structure, the first dislocation can destroy that ordered structure, creating a softened plane that the next dislocations find it easy to follow. That's the theory. That's the theory. And in the field of metallurgy, there's been a lot of work recently in something called high entropy alloys, where you have a mixture of many different elements, usually equally atomic. And in that case, there's a real, important question of whether there is local ordering in these alloys. They're thought to be sort of homogeneously mixed up. All the atoms go different. It doesn't really matter where the atoms are, but the ordering could have a really important effect, like something like this. So, just to give you an idea of the field of high entropy alloys, high medium entropy alloys, the word entropy comes from the fact that you have a configurational entropy. If you have 5 atoms, 5 different elements, and you mix them 20% each you have a high amount of configurational entropy. It's kind of not a great term, but it's sort of stuck for these alloys. And they have really really great properties. So for instance, one property that's important for fracture toughness is fracture toughness in an alloy. And the high entropy alloys have among the highest fracture toughnesses of any alloys so far. And so one of the questions is, does short range order contribute to this? And I'm going to sort of walk you through this and sort of try to explain how it does. First off, can you see short range order? Well, one way that we started looking at short range order was with energy filtered TM. And with energy filtered TM, you get you decrease the inelastic scattering by having a filter. And what that gives you then is the ability to pick out weak superlattice spots that come about from short range order. So for instance, that's shown here, a weak superlattice spot. If you do a dark field, you can actually visualize all these little bits of short range order domains. In a medium entropy alloy, so this is what's called the cobalt chromium nickel, so 1/3, 1/3, 1/3 is a composition, all mixed together. This is sort of the standard highest performing FCC medium entropy alloy. And what you see is, for instance, streaking depending on how the sample is processed. And that streaking comes from, if you use a dark field, regions of presumably local order. That's what's shown here. And you can sort of see this in high resolution. Of course, these elements, chromium, cobalt, nickel, are all right next to each other in a periodic table, so you don't get essentially any Z contrast. You can't really get anything from STEM out of these materials. But with a little bit of phase contrast in TM, you can start to see regions where you have, you can see these sort of bright lines that represent on the 111 planes that give you same, in FFT also give you the streaking, so you kind of see these things, but it's really a difficult thing to visualize without this energy filter TM, essentially dark field analysis. But by doing that, by putting your apertures here, you can see these blobs of regions of order, and you can quantify it. And so the dimensions are about 1 nanometer, which is what's sort of predicted. So it's a few unit cells of order and some C of disorder. And one question then is how does these order domains affect the properties? Well, to get a little deeper into the metallurgy here, one of the useful ways to describe defects in metals is something called the stacking fault energy. Stacking fault energy is the energy, the local energy in this term here for nominally defect-free FCC material to form a stacking fault. And a stacking fault, a single layer stacking fault in FCC is actually HCP. So you can think of a stacking fault energy as saying, what's my tolerance for having a little bit of HCP in my material that nominally wants to be FCC? Well, what was really interesting in this alloy system a few years ago is my colleagues Mark Asta and Rob Ritchie, using DFT, they calculated what the stacking fault energy was of this medium entropy alloy. And they found that it was negative, which means this alloy that is FCC, face-centered cubic, actually really wants to be HCP. It wants to be a different crystal structure, but somehow it's FCC. And so the question is how? How is it stabilized? And the prediction is that short-range order stabilizes this FCC. So little bits of short-range order help to overcome this negative stacking fault energy. And so you can quantitatively, experimentally measure stacking fault energy. There's a couple different ways. The most common way is by measuring the distance between partial dislocations, because between two partial dislocations is a stacking fault. And by measuring that width, you actually can back out through a simple equation shown here, what's this actual stacking fault energy. And so we did this in this medium entropy alloy, and we did this in two different conditions. One's water quenched, so take the sample up, quench it, and the other one's aged. And presumably a sample that's been aged has more short-range order in it. And then you can see here that in dark field you can see the two partials, and you can measure that distance from the two partial dislocations, and you can plot that separation right here. So the water quenched has a larger separation, which leads to a smaller stacking fault energy. And the aged has a smaller distance, which leads to a larger stacking fault energy. And this is sort of showing you that, yeah, if you quench it, it's got a smaller stacking fault energy. So this is not negative, but you're getting closer to the negative as you quench in that structure. So it's consistent with this idea. But it's not quite the full story, right? So I want to try to tie this now to the deformation feature. And we most recently did that by trying to deform this material in situ and use 40 STEM to look at the defect structure and how it comes about in this medium entropy alloy. So 40 STEM, you can also, of course, do this in situ. And you basically take stacks of diffraction patterns, and you can either do this while you're deforming the material and just sort of doing a continual way, or you can stop and then take a set of diffraction patterns at some point. So I'll show you some mechanical tests where we did 40 STEM during this test. I first want to mention, well, Colin mentioned this yesterday, so I'm not going to go into detail, but so let me go back up. These experiments are complicated. There's a ton of data. You don't get to pick your diffraction condition and the tilt and all this stuff, so it's quite messy. And so it's really only with these tools that Colin and his group have really developed recently that we can do this. For instance, the automated analysis with Pi40 STEM. If you didn't have this package, you really couldn't analyze these huge amounts of data. The apertures that Colin talked about yesterday, enhancing the strain position, enhancing the strain. Again, you really couldn't do this because one of the biggest impacts of these bulge apertures is actually in thick samples. So you see here the difference between a thin and a thick sample in terms of the cross validation error, which is, as Colin described yesterday, if you index one half of the diffraction pattern and say how well does that predict the other half of the diffraction pattern, you see in the thin sample you go from, let's say, 3% down to 0.6%, but in the thick sample you get a huge increase in your accuracy and your precision from these bulge apertures. And in an in situ experiment, you're always with the thick sample. You're always with the thick sample, or else things will just break. So you always have a thick sample. And another big improvement that to these types of experiments is energy filtered 40 STEM. So again, thick samples. And so the experiments I'm going to show you were all done with our new K3 at the back of our continuum GIF, so that we can actually clean up our diffraction patterns, and so you get it's much easier to analyze, even if you're not in a perfect zone axis, for instance. So the experiments that have started to work the best for us are experiments looking at fatigue. One of the reasons is that tensile tests, if you just take a sample and just pull it apart, is kind of chaotic, and you don't really see a lot. It's just things just break, especially when you get down to these thin dimensions. But fatigue is good because you basically have sort of a stable deformation that you can control. And so the way we do these experiments is use what's called a push-to-pull tester. So this is a little MEMS type device, or a little microfabricated silicon device. If you push on this knob here, this part of this device is pulled apart. So you can imagine you push here, and it turns the pushing into a pulling. So if you put something across this gap right here, you pull it, and that's what's shown here. So here's a metal foil, the jet polished high entropy alloy, medium entropy alloy foil, where we pulled it out with a fib, only fibbed the sides, and we fibbed in a little crack. You know exactly where the deformation is going to start.
What is the scale bar because it's covered?
Yeah, good question. This is a couple microns, this gap. So that's 1 micron is that thing. 1 micron. And so you can see you can do a fatigue test as shown here. And while we're doing the fatigue test, we can take diffraction patterns. And this is what the diffraction patterns look like from this experiment. What's interesting is you've got your Bragg diffraction, but you have clear streaking in the one-to-one directions during the deformation. And I'll show you what those are. And what they are stacking faults. or twins or HCP. All those things will give you scattering along this direction. So trying to discern all that stuff is part of the fun. But if you, for instance, put a virtual aperture along these streaking regions, you can visualize the parts from 40 STEM, the parts of your sample that are giving you the streaking. So these are some sort of faults or HCP that's existing inside this nominally FCC single phase material. So here's an experiment. So here's the crack tip shown here. Here's the 40 STEM region. There's the strain field. So again, every pixel we have a diffraction pattern. This top row here is just using that streaking to make a virtual dark field. The bottom is your strain field from just indexing the last parameters of your diffraction pattern. And what's interesting here is you see as you load it up, you open up the crack, you get the streaks, and then you unload it and they go away. So this is pretty interesting. So basically, the interpretation is they have a partial dislocation that goes out, and then it zips back, closes. And so that's the first step, and then here's 1,000 steps later. We didn't take data at every point, just did the first few and then skip to 1,000. And what you see is this, well, okay, it's all washed out here, but it's exactly what I showed you before. You got just a couple of things, they disappear, and then eventually they're permanent. So eventually you get these permanent lines in the scientific reality that are coming out, showing you that you've basically cleared out some sort of, presumably some short range order, and you've got now this permanent feature that is really a small, thin stacking fault. So we wanted to compare this to something. And so the thing we compared it to was a pure metal, nickel. Same exact experiment here, and it's pretty washed out, but you don't see the same features. Instead, you get local deformation, little defects that are permanent from the very beginning. You don't get the long partial dislocation, long stacking faults. You just get localized deformation around the crack tip. And so a cartoon, a schematic of what the difference is between the medium entropy alloy and the nickel is shown here. In the medium entropy alloy, presumably you start with little bits of short range order. You clear them out, sort of one dislocation by one dislocation, and so you end up with these long, extended, thin defects, which are great for work hardening. That's exactly what you want if you want some barriers to motion, as opposed to a pure material which has localized, permanent, but not extended defects. And this is what's seen in the literature too, from ex situ experiments. This is the same exact alloy, ex situ fatigued, then looked at atomic resolution. This is a paper by Mike Mills' group at Ohio State, and it's the same thing. So he's now looking at ex situ, the type of defect structures in this fatigued sample, and you see same thing, these long extended defects that are essentially all the different variations of stacking you can have along the 1-1-1 direction. So you can have a single stacking fault, an intrinsic stacking fault, you can have an extrinsic stacking fault, you can have a nano twin, you can have little bits that you can characterize as HCP. It really just, these are all sort of variations of the same thing, how you change the stacking, which, one partial dislocation at a time. And all of these are very good barriers very good for work hardening. And so we wanted to look at then, okay, let's say you put these structures into your material. How does this then affect your fracture toughness? How did you actually, why are these barriers so good for fracture toughness? And so we did the same experiment, but now we took a foil, we took our sample from a region that's already been highly deformed, so a fatigue crack itself. We put it in the TM, same thing. We put a crack in a sample that was already had lots of twins in it. And what you see in the deformation, I thought I had a movie. Oh, a little out of order, sorry. Here's the movie. Well, you can't see it here, but what you see is little, more stacking faults coming in, this network increasing. and, oops, sorry, it's backwards. And eventually you get this pretty dramatic crack deflection along a twin boundary. And this is a thin foil, so the constraints are different than a bulk material, all that kind of stuff. But what's quite interesting is, if you're thinking about how do you stop a crack, this is what you want. You want things to crack to change its direction, because that's basically slowing down that crack. And that's what's leading to toughness in the material. So you sort of see it right here. You see it, this is the same sample, this dramatic crack deflection. We see that also in MD simulations of samples that have these thin twins in it. You get this separation of twins and also this crack deflection. And so, what we think is that one of the reasons that the short range order leads to enhanced fracture toughness is because of this idea that you get these extended defects because of this clearing out of short range order. And in a material like pure nickel, where you don't have short range order, you have a high stacking fault energy, and these dislocations tend to stay together, and you don't get these long extended defects. And these long extended defects are what's really great for toughness. And just to prove that point, this is my last slide here. This is a paper that was just accepted in Science, because this is the same alloy, and we recorded the highest fracture toughness ever, essentially. So the same alloy at low temperature, 20K, near liquid helium, has this fracture toughness above 500, which is a crazy number. And it really comes about from what we think is these long extended defects. And it's in this paper, we actually use 40STEM to visualize these little bits of HCP, little bits of twins and stacking faults. And I would argue that there's really no other way to do this, because the microstructure is absolutely crazy, right? This is bonkers. How do you describe what the heck's going on in here? The defect density is so high. This is what bright fields look like. How do you describe what this is? And with 40STEM, you can actually start to pick out different parts of this, highly deformed network and say what's there. Well, what's there is sometimes twins, sometimes stacking faults, sometimes little bits of thin bits of HCP. And so 40STEM, I think, was critical for us being able to describe why you get this incredibly high fracture toughness in this material. Okay, so again, just full circle, microstructure is incredibly important to relating to properties, and 40STEM is a critical tool at this length scale. EBSD, like I said, is the standard in metallurgy, and that's what's shown here. But the key is EBSD cannot pick this stuff up, and really only 40STEM can pick this up. Yeah, Juan.
Out of curiosity, so usually what is the average of the toughness for these kind of materials, for metals? I mean, I don't know, because you say 500, but... Yeah, what, above, look, anything above 100 is pretty good. Steels are up in these, there's cryogenic steels that are up in these high numbers here. Another thing that's interesting about this alloy, it's not unique to high entropy alloys, but a lot of materials get brittle at low temperature, right? You think of fracture, ductile or brittle transformation temperature, a lot of materials get brittle. Materials that twin, like HCP materials and like FCC, that's bordering on HCP like this, materials that twin tend to actually increase their toughness, increase their strength at low temperature, because twinning is a really excellent hardening feature. So, what's a good number? Well, anything above 100, but 500 is really crazy, and especially for a low temperature material, low temperature. Okay, so with that, my talk, TBA, I'm not sure what TBA stands for, but I will say 40STEM enables quantification of microstructure across multiple length scales. And I just want to thank all the folks that did this work. Postdocs like Shatang and Ripeng worked on the high entropy alloy stuff, and Yang. Steve, who's here, of course, worked on the bullseye aperture stuff. Jen worked on the polymer work recently, and then all this is in collaboration with folks at NSEM like Karen and Jim, my colleagues on campus, Daryl, Mark, and Rob, and of course Colin, who's the center of all this 40 STEM business at NSEM. Yeah, so with that, thanks. I'll take any questions.